remote?
Yes.
That'll work?
Use the big
Great.
arrows.
And there's a pointer?
Yes.
Great, thank you. Great. I'm happy to be here. I'm a big fan of the SBIR program, and even more so now because they've added Search for Life on Ocean Worlds in several of the topics, and that's what I'm going to talk about. So the title is Europa, Ocean Worlds and Life Detection, and the subtopic is Searching for a Second Genesis of Life. And that, in some sense, is the theme, one of the key themes of astrobiology, is searching for example of life on other worlds, and the hope that the example we find is different than what we have here on Earth, what one might call a second genesis. Getting to two would be great. Just real quickly, in the old days, we used to focus on the Earth, Mars, and the ancient Earth 3 billion years ago, as the scope for astrobiology. Those were the worlds that were interesting. When I got interested in astrobiology, those were the places that we studied, Earth, early Earth, and Mars. But in the last couple decades, we've realized that the moons of the outer solar system are really quite interesting from an astrobiology point of view because they have liquids. A lot of them have liquids as water, particularly Europa and Enceladus. And there's other liquids out there, as we'll see on Titan. There's liquid methane and ethane on the surface. So there's been a new domain of interest added to astrobiology in the search for life, the outer solar system. It's being called within NASA the Ocean Worlds program. So if you're searching through calls or announcements, it'll be classified as Ocean Worlds. And of course, part of all NASA activities are rooted in official documents. When you write proposals, you have to open up with this official document says that the country ought to be doing what I'm proposing to do. So the most official documents are the Decadal Survey. The recent one, the one that's operative now, calls for the search for life elsewhere in our solar system. So these words get quoted in all the proposals I write. We're going to address the Decadal Survey goal of searching for life elsewhere. Do organisms live there now? In particular, NASA released a big call for missions, the billion-dollar class missions, New Frontiers. Those proposals were due just a month ago, and Ocean Worlds was explicitly included in it. And Enceladus is ocean, was called out, assess the habitability of that ocean, and search for signs of life in that ocean. This is the first call for a NASA mission since 1970s that includes the search for life as an explicit goal. It also includes Titan to understand its liquid cycles, liquid methane. So that's the New Frontiers call. Missions may be selected to these targets as a result of selections to the next step in that call. In addition, NASA has a directed mission planned, not a competed mission like the New Frontiers, but a directed mission plan to land on the surface of Europa. And its science goals taken from the preliminary call are to search for evidence of life on Europa. So this is another mission which has explicitly in its goals search for evidence of life. Assess the habitability, characterize the surface, and here's an artist's conception of that lander on Europa with a very optimistic plume in the background. Would that Europa had such plume activity on a regular basis? So what does NASA need to do this? NASA needs technologies for collecting samples from icy surfaces, from plumes in space that are jetting out from these worlds. We see them in Enceladus. We hope that they're on Europa, and from getting samples from below ice covers in cold vacuum conditions. Okay, NASA needs technologies for extracting biomarkers from the sample. We're not going there to collect ice. Well, sorry, we're not going there to study ice. We're going to collect the ice, but then we want to extract the biomarkers from that ice. NASA needs technologies for identifying these biomarkers. How do you tell a biomarker from inorganically or abiologically produced organic material? And improve technologies for spacecraft operation in the outer solar system. The outer solar system is a tough place to work. It takes a long time to get there. Solar energy is very weak. It's very cold. There's no atmosphere for aerobraking if you're going to land on moon moons like Europa and Enceladus. There's a lot of challenges flying through these plumes. For example, Enceladus, if you just go there in a simple trajectory, your relative velocity with respect to the plume as you fly through can be up to 5 to 10 kilometers per second. So how do you collect a sample moving that fast without completely destroying the things in the sample you're trying to go there to collect? Right? So how can small businesses help? My personal view is that we need all the help and innovation we can get, because what we're trying to do, life detection, NASA's last and only life detection mission was Viking in 1976. So we are now doing something that we haven't done since 1976, and few of us were around back then. Remember, and even if we did, it doesn't matter, because the way we did it, Viking, is no longer relevant. Viking was a culture-based method to search for life. It basically took Martian soil and put it in with soup to see if anybody would eat the soup. Right? And we only made a detection if the organisms ate the soup. So that's what microbiologists nowadays call growth-based methods or culture-based methods. No one is proposing to use that now for life detection. So you only detected things that were alive, and you only detected things that were alive and liked to eat what you fed them. Right? If any of you have children, you know that this is not a very good test. Right? So the question we're now faced with is, how do we search for life on other worlds using new technologies, using powerful new biotechnologies? That sounds great, but the problem is these powerful new biotechnologies are finely tuned for Earth biochemistry, usually medical applications. So adapting them to a generalized life detection is not easy, and that's why we need help and innovation. And we have specific and unique problems in the outer solar system that we don't have in biotechnology, like just storing the reagents 5 to 10 years as you fly out there before you use them. Right? A lot of times in these new technologies, you make the reagents fresh and use it within a few hours. Right? Well, we've got 5, 10-year flight times before things are used, not to mention the radiation and other exposures. So it's going to take, we can't just go order biomedical kits off the shelf and plop them in the spacecraft. There's a lot of work and technology that needs to be done to make those life detection methods work. And biotech approaches and instrument concepts from small companies are highly relevant here. So that's why I'm excited about SBIR and the opportunity to talk to that community about life detection. So let me quickly point out the targets. This is Europa. Europa is one of the Galilean moons of Jupiter. It's the bright one. You can recognize it with this telescope. Go to an amateur astronomy night, look through a telescope, look at the Galilean moons. Europa is brighter than the others because its surface is resurfaced with ice and snow. It's very, very white. There's Io, Ganymede, and Callisto, but Europa is the one that we have, that we believe we're sure has an ocean. We think that ocean is accessible under a few kilometers of ice. You know, getting through ice kilometers thick is not easy, but it's there. We know that the ocean's there from the surface morphologies, icebergs sticking up indicating frozen liquid, that these icebergs were floating on a frozen liquid. The evidence that the ocean is there now, today, comes at, interestingly, from a magnetometer. As Europa moves through Jupiter's magnetic field, it distorts that magnetic field, and that induces a magnetic the current in Europa, indicating a conductor, a large conductor in Europa, which obviously is a salty ocean. So that the evidence for an ocean comes from a magnetometer, which is an interesting thing. You wouldn't expect a magnetometer to be a key astrobiology instrument. The problem with Europa is getting to that ocean. There's cracks on the surface. Well, there are features on the surface that may be cracks. If they are cracks, maybe there are ocean materials coming up through that crack, and we can sample that. Maybe there's also 2 reports from telescopic observations from Earth of clouds around Europa that have been optimistically interpreted as plumes coming from the ocean. Maybe you could fly through that and sample it. Europa, I think, is going to be a very, very hard nut to crack. Getting samples of the water, accessing it is going to be very difficult. It's a severe challenge. As I said earlier, what NASA is currently planning to do is just land on the surface. That's kind of the Hail Mary pass in terms of going to Europa. Hope that you find something. Saturn's system is more promising. Enceladus, the small moon that creates the E-ring, has been thought for a long time to have outgassing because the E-ring is unstable. It was first observed in the 60s, and the inference was that Enceladus must be doing something to create that E-ring around Saturn. And sure enough, Cassini got there, and in 2005 discovered these really phenomenal jets of icy water coming out from the south pole of Enceladus. A flux of liquid comparable to the flux of liquid from Old Faithful Geyser. This is water shooting out. And it's not just water, it's water coming from a hydrothermal system below the ice from a deep ocean. And most interestingly, and we could learn this just from the Cassini instruments, that water has organics in it. It's not water, it's soup. Right? Soup's on at Enceladus. Right? All the ingredients for life are there. Nitrogen in a biological form, carbon, energy sources in terms of hydrogen and CO2 suitable for microorganisms. All the main requirements for life are met in the plume, and the samples are coming out. Free samples, grab one. Although free is not quite as free as you think, because you got to fly out there and then you got to slow down and get it. How, if we got samples, how would we analyze them? One approach, well, the general approach is to look at the biomolecules that life makes. And I want to illustrate that with a particular molecule, amino acids. As you probably all know, life on Earth, all life on Earth, uses only left-handed amino acids in constructing proteins. So all the proteins in your body and all the microbes in your body are all made out of proteins with left-handed amino acids, not right-handed amino acids. So biology has done a major selectivity on the amino acids it uses in making proteins. When we make proteins in a chemical experiment, we make roughly the same amount of right and left. Chemistry doesn't care about right and left, but biology does. So one approach is to go to Enceladus, collect amino acids, and determine whether there's a predominance of one-handedness over the other. On Earth, we're all left-handed. Wouldn't it be cool if on Enceladus the life there was right-handed? Just for a little diversity, right? We're all about diversity. So then the question is, well, how do you detect that? That's a real instrument challenge. They are identical in terms of their mass spectrum. A left hand and a right hand weigh the same thing. The only way you can tell the difference is if you've got some analysis that's sensitive to the shape of the molecule, not its mass. So right now, the way we propose to do this is really clunky. We take the sample, we put it through a column that has a chiral selectivity, separate them, and then measure the mass. Okay, is there a more difficult way to do it? Probably, but hopefully there's also a lot more easy ways to do it. There are some distinct spectral differences in terms of circular polarized light and things like that that might allow us to more simply and directly measure the chiral excess in a sample. So that's my hope, is that we come up with these new technologies now that we're getting serious about life detection. Okay, quickly now to Titan. Titan is a world apart, really, so to speak. It's really a moon, but it's a world apart because it's got a liquid. It's the only world besides the Earth that has beaches, right? Waves coming up on the shore, sky, clouds, nice, beautiful scene. Don't imagine you're there on a towel with a lemonade, though, because the temperature is minus 200 centigrade, which is minus a lot Fahrenheit, too. So it's really cold because that liquid is liquid methane. It looks like water. It's clear. It behaves like water. The clouds look like water clouds. It's a picture-perfect representation of Earth, but it's 200 degrees colder because it's liquid methane. But it's a liquid. And many astrobiologists are excited about this because maybe this liquid could support life. I mean, what's so special about water? What's special about water is it's a liquid. So maybe a liquid on Titan could support life. This obviously is not Titan. This is a Lake Mead near Las Vegas. And the film crew was filming me standing there. And this is how they rendered it to look like Titan. But there are really lakes on Titan. These are the lakes in the North Polar regions of Titan. They are the size of the Great Lakes on Earth. Right? Could there be, how would we detect life on Titan? The key, I think, is energy. One thing we know that life is going to need anywhere is energy. Life on Titan is not going to use amino acids. We can't use a biochemistry-based approach tied to Earth biochemistry. Amino acids are useless in liquid methane at cryogenic temperatures. But the one thing we can say with absolute certainty, based on the first law of thermodynamics, is that life is going to need energy no matter where it is. And what's the energy source on Titan? I think we've concluded that it's going to be hydrogen. Organisms can consume hydrogen, and that's a source of energy, chemical energy on Titan. So it could be that where on Earth, life is widespread, and what it consumes and produces therefore creates a global effect. So life is carbon-based, lives in liquid water, and is widespread. And so it creates gases like oxygen, methane, and CO2 that you can detect in the atmosphere. So if you were an alien spacecraft and you came and landed on Earth, just detecting the gases in our atmosphere would tell you that there was life on Earth. Right? Oxygen, methane, and CO2 as an example. Same thing we could apply on Titan. Life on Titan would be carbon-based, liquid methane instead of liquid water. If it was widespread, what would its global effect be? And I think one conclusion is that its global effect would be, it would be eating H2. So you'd see changes in H2 just like you would on Earth. If you track CO2, in spring when the plants consume CO2, it goes down. In fall when the plants shed their leaves and the CO2 is produced, it goes up. That up and down is a seasonal signature of life on Earth. There might be similar seasonal signatures of consumption of hydrogen on Titan. So the prediction is with no life, hydrogen is constant. With life, there's a drop near the surface as the organisms are consuming, and this might go back and forth. Measuring hydrogen is an example. It's a very easy measurement to make on Earth. But if you look at the technologies that are available, they are tied to two particular properties of Earth. One is the presence of oxygen to desaturate the sensor, and second is high temperature so that the kinetics are reasonable and you can make the measurement in less than the lifetime of the mission. On Titan, we don't have oxygen and the temperatures are cryogenic. None of the hydrogen sensors you can buy off the shelf work. So this is another example where a life detection mission, indirect life detection on Titan, would benefit from a starting base of Earth technology for hydrogen detection, but there needs to be some innovation and change to make it work for the space conditions. And of course, don't ever forget the 10-year storage time to get there. All right, I want to end hopefully early so that by pointing back to Earth and saying that we have an enormous understanding of life on Earth and an enormous technology base for studying and analyzing that life on Earth, which has taken enormous advances over the last 4 decades since Viking. So we should be in a much better position to go forth and do new instrumentation and new missions for life detection. And the ocean worlds are calling. They're not only calling, they're funded. So it's time to get serious about that. And that's why it's a pleasure to be here. And I'll end by early, I hope, and have time for lots of questions and discussion. Thank you.
Finding life.
How am I defining life? That's a really good question. And the answer is we don't know. We don't have a useful or consensus definition of life. But to quote that famous Supreme Court ruling, we can't define it, but we know it when we see it. So that's our approach. And here, let me give you an example. If we were to go to Enceladus and in the plume find complex, well, take the simple case I showed, find that all the amino acids there are right-handed and that there's a set of 20 of them in the plume and they're all right-handed, all 20 of them. That is just statistically very, very unlikely to be random. So that means something in there like life is selecting for right.
So this is based on Earth chemistry and Earth understanding.
For Enceladus, which is a water world. Yeah, for Titan, it's more hard because there's not water, so we don't really know. So, but the general answer is we look for distribution of molecules which by their size and properties are just not likely to have been produced non-biologically and indicate that there is a biological selectivity at work.
Are you considering it might be different on Earth?
I'm hoping it might be different. As I said at the very beginning, what we're hoping to find is a second genesis of life. So we want it to be different, but we want it to be similar enough that we could recognize it. So that's why the right-left is important. If we go to Enceladus and we find amino acids, we can recognize them. If they're all right instead of left, that's different enough that we know that it's a second.
Okay, so my last
genesis
question is, would it be worth it to fly along with all these, organic detecting type instruments and so forth, to fly sensors that look at the electromagnetic radiation? I mean, you're already doing that, but to look at things that are not normally looked at, as far as, take it at a more advanced level. If there was an alien species that existed on that planet that had intelligence, and maybe even had a civilization that you can't even see, you may be able to pick up some of their communications. So having that little extra piece in there while you're doing all this science stuff might actually give you a quicker answer in some cases, just by flying over the atmosphere. If there's something going on there, you can tell immediately there's some kind of intelligent life. So I would say don't forget that little piece.
Well, let me answer that in two ways. One is, there's certainly interesting to search for intelligent signals and intelligent life. But our reconnaissance of the solar system means that in our solar system, that's very unlikely. For exoplanets, it's a whole different story. So we find planets around other stars. We would be wise to do just what you're saying, is to search for signals. And people are doing that. Unfortunately, we can't go to those worlds. But with radio telescopes, we can look for signals. In our solar system, it doesn't look, it's pretty clear from the reconnaissance. It's unlikely, but not impossible, but I would think that there's still an application for sort of the logic you're proposing, which is looking for spectral changes and spectral signatures. And spectroscopy is a good example. I'll pick out one particular molecule I happen to like, ATP. I use it every day. And it's got strong fluorescence bands. And so just with a spectrometer and a laser, you can detect it without actually even picking up a sample. So it goes back, let me generalize the point, innovation and new ideas for how we're going to do these detections is useful. And if you can add a rider, or add a little something on that without much cost or implication scans the electromagnetic spectrum for unexpected signals, why not do it? Other questions? Oh, so it's follow the square. Okay.
Yeah, following the cube.
Yeah.
Two-part question. One, has there been any topic broached as to the possibility of investigating silicon-based life? And part two, has the topic been broached about potentially creating our own soup or our own genesis by bringing our own creation of life to implant on another planet?
Right. Let me start with the second one first. There are people, scientists in the lab trying to create life from scratch. They're also trying to create what they call artificial life by working down from the life we have. And that may be, in fact, where we first get a second example of life, is make it in the lab. For example, you could imagine taking the blueprint of a cell, a very simple cell, and creating it mirror image. So you make the D version of all the amino acids and the L version of all the sugars. So it's exactly the mirror image. I think there's a Star Trek episode that's centered on that, right? Hooray for the original series. So and that would be a second genesis and an artificial one. I view that as the competition, by the way. They might succeed in getting a second genesis first, but we might find it on Enceladus or Europa first. Or we might get an intelligence signal from a distant star, and then we can ask them, is your DNA like our DNA? We'll show you yours if you show us ours. We'll show you ours if you show us yours. So there's this race to find another type of life. But I'm pretty optimistic that Enceladus, Europa, and even ancient Mars may be good places to go search. So I think let's go search. Your first question is, what about searching really strange? So on Europa and Enceladus and Mars, really, we're looking for life like Earth that makes its home in water. And that defines the capabilities. It's going to be amino acids. It's not just carbon, but it's going to be amino acids. You would be a fool to live in water and not build yourself out of amino acids. On Titan, we have a liquid. It's liquid methane. Amino acids don't work. We don't know what does work. If there's life on Titan, we have no idea what its building blocks are. We can only say general things about it, like it conserves energy and therefore must have a source of energy. We can probably say it's made out of carbon because that's what's abundant on that world. There's nowhere in our solar system where we can motivate a search for anything different than that, where we could say, well, look, here's a world where carbon or silicon is doing interesting things. Let's go check out that. At least I haven't been able to find it. So we don't have a good rationale for proposing a mission to search for anything beyond Titan in terms of strangeness. And even Titan is on the edge. I'm not sure it would pass non-advocacy peer review going to Titan to search for life. So we would disguise it as going there to search for hydrogen and its variations, knowing that if we see a puzzling signal, it would then spark interest in life. So, but that doesn't mean that the question is nonsensical. It just means that in our solar system, we don't have clear opportunities. I think it would be premature to conclude that life as we see it and know it is the only example. We have no idea. When you have one data point, your knowledge base is extremely limited. We may turn out to be the unusual. We may turn out to be the freaks of the universe. It may be that all the silicon life forms from all over will fly to Earth to see this strange, gooey, slimy, smelly, carbon-based life form, right? So who's to say what's typical and what isn't when you only have one data point? It's sort of like if you're the only one, you're normal, right? Okay, other questions?
We have a virtual question. Do you need sterilization technologies to make sure we don't contaminate the environments out there?
Oh yes, that's very good. I should have put that on my list. In fact, I did. It was on my list. Contamination. Without contamination, that's very hard to do. And what's happening is our instruments are getting so sensitive that even dead microorganisms on our spacecraft, if they get swept into the instrument, could give us a false positive. And so if you go to Enceladus and find evidence for life and you want to publish that paper, we have discovered the first evidence of life beyond the Earth. You've got to have the controls done very well. And that's contamination control. You have to figure out how do you do a in situ negative control. So when if you go through the plume, you see a signal, you've got to run a sample where you don't see a signal. So you know it's not an artifact of your instrument. I think I put this, let me go back to that list because these items are on that list. Because this is a very important point, and it's a point that right now I'm worrying about an Enceladus mission, and these points are bothering us. The problems are 5 to 10 years in space, prevent contamination, confirmation bias. But this is the view that it's becoming a big problem in astrobiology. You're so enthusiastic about the answer that you want to get, that you ignore all the data that doesn't point to that answer and embrace the data that does. And psychologists call this confirmation bias. Reviewers just call it stupid and reject your paper, right? Or false negatives. You also don't want to fly to Enceladus and not be able to detect the life that's there because your instrument isn't general enough or broad enough. So these are very important points, and we don't yet have good solutions for them because we've never done this before. I keep going back to, it's been 40 years since we tried, and we tried with technology that was 40 years prevalent at that time. This is a whole new ballgame.
Since we've already sent probes that far, and they have taken a long time to get there, do we have a database that tells us just how possible it is that we might have contamination or confirmation bias or false negatives after 5 to 10 years flying in deep space and high radiation?
To some extent we do, but to a large extent we don't because the instruments that are on these missions are not the life detection instruments we're now flying. So, Cassini has a mass spec, and they worry about contamination, but the mass spec on Cassini is not the mass spec we would fly on a life detection mission. The instrument we would propose on a life detection mission is much more sensitive. It has to be. So we don't have a direct database, so unfortunately. And we need to develop that with simulations on Earth and also with missions, with experience with missions.
Hey, Chris.
Hi, Rich.
Hi. Could you talk a little bit in terms of the SBIR community, what small businesses might be able to do, the kind of the process of sample collection, sample concentration, and then detection, and how what finite chunk of that we might have small businesses. In particular, I know that we want to, life detection is complex, and it somehow depends on what you're going to do next depends on what happened last.
Right.
So we're really looking at complex protocols
Right.
and how we might incorporate that kind of new way of doing business.
Yeah, it is a good point, Rich, and I'd say once again that the ocean world's life detection was in the last year's call for step one, for phase one, and was divided roughly the way I've divided it here. Technologies for collecting samples. One of the important points is the sample size we need is very, very small. To do life detection, the sample size we're talking about is very small. So we're not talking about big instruments. We're talking about small devices that are winning because they're innovative. But we're, for example, as I said, moving through plumes at high velocity. We're trying to get samples, to get a little tiny bit of a sample of an icy surface where the ice is at, say, 90 Kelvin. Then we want to be able to take that ice, that sample, and extract the biomarkers. Let's take the simple case. You've got a sample of ice, and it has frozen in it amino acids at a part per billion level. Right? How do you get that sample, that amino acid, from a small amount out of that sample of ice? How do you separate that? So extracting biomarkers from the sample. And then methods for identifying them. As we talked earlier, let's say you're focusing on the right and left-handedness. Is there some way to do that directly? For example, polarized light interacts differently with the different handednesses. So maybe there's some way to look at the sample without doing any extraction, but just probe it with lasers and polarized light. So there's a lot of specific questions, and I've illustrated some answers, but there's going to be a whole range of approaches that we haven't considered yet, and they're going to come from out of the blue. Material scientists who are doing laser characterization of surfaces are going to realize that their technologies can apply to detection of biomolecules in an ice water sample with wavelengths that transmit through the water. I don't know, I just made that up. But the point is that there's a lot of ways in these, from collecting the sample, extracting the markers, identify them. And of course, generic call for spacecraft, power systems, data systems, lower power, cold tolerant. For example, I'm trying to think about a hydrogen sensor on Titan. It would be great if it could operate at Titan temperature, right? So you didn't have to spend power to heat it. So make it operate at 95 Kelvin. So start with that design. That's not something you normally do on Earth. But there are some applications where cryogenic instrumentation is used on Earth. Can we benefit from that technology? And again, I don't see any of these things as beyond the scope of small companies. And in fact, a lot of them are perfect fits for small companies.
Yeah, hi, Chris. Just a comment that, people might think this is so out of, far away to do things. There's already SBIRs where companies have proposed drills to go through, the ice layers, the 10 kilometers or 20, whatever it is. And the company is also selling this technology to oil exploration. So there's actually very nice fits, and it's doable. We have SBIRs that are proposed actually to help out doing this. So just a comment.
Yeah, there's a current SBIR that was selected last step that will develop or propose to develop a ice gun, ice jet, that will allow us to simulate the plume. So they're basically a device that allow us to spray ice particles of the micron size, a kilometer per second, so that we have a laboratory capability to test instruments. So there's a lot of aspects to this, and they're described in the SBIR call. Several were selected last cycle.
We have a question from the virtual participant. What about the design, regarding the drills, what about the design for an ice drill that allows the walls to reharden behind it so it does not need a miles-long tether, just communicate up through the empty column?
Right. That's an interesting idea. On Earth, of course, when we drill, usually there's a long string or tubing coring that goes down. And that's because Earth is sopping wet and water will flow in unless you case the hole, so it's problematic. On icy worlds like Europa, this should be a lot easier because if you drill the ice is as hard as rock and it's not going to melt. Temperatures are 90 Kelvin. It's not going to turn to water. It's like drilling through, it's more like cutting through wood. If you thermally melt, as opposed to mechanically, it will sublime. It doesn't go to liquid, it turns to vapor. And so this is true on Mars as well. So there are some differences in the physics, that can make the problem, that can be used to leverage solutions that we wouldn't think of on Earth. And there has been work doing that. And I know there's been SBIRs focused on that, companies looking at drilling under low pressure and low temperature conditions.
So there's a follow-up question to this one. Could you use materials from a small moon to make drill tube sections on the surface as well as way of retrieving the ice core? Considerations regarding what could happen once you poke a hole all the way to the ocean, especially as it's probably under pressure.
Right. What happens when you poke a hole? I'd like to be there when we do that, just to see the geyser that comes up. Probably, I'm guessing, but probably if you poke a hole all the way to the ocean, you will get what we're seeing on Enceladus, a plume coming out into space, because you have the vacuum of space with zero pressure, and you've got water, which at minimum has got its vapor pressure, 6 millibars. So there's a pressure differential. You drill a hole, first buoyancy will bring it up to 90% of the level of the ice, and then out it's going to come. So maybe the solution is drill the hole, step back, and just catch it as it comes down. I'm focusing more on near-term missions where drilling through many kilometers is probably not within scope, but it's fun to think about it. All right, I think we're running close on time.
Not yet.
Oh, okay. Darn.
We have 6 more minutes.
Okay.
We have
Great.
a few more questions. Online participants are really excited about this session for sure. Are miniature mass spectrometers of interest? If so, what mass range?
Mass spectrometers. Mass spectrometers are always of interest. A mass spectrometer has been the workhorse of organic analysis in the space program. And they are useful in life detection in two ways that come to my mind, but probably people can think of other ways. One, in characterizing the mass spectrum of lipids. Lipids are molecules that occur in biology that have a distinctive pattern due to biology. So the mass spectrum of lipids, and then the mass range is from a few mass, 10 maybe atomic mass units up to thousands, because these lipids can be quite big. Another role of mass spectrometers in life detection is on the detection end of a column. So you can imagine a column tube in which the gases are, the samples put in, the right and left molecules, amino acids are separated, and as they come out, they're detected with the mass spectrometer. So it's being used as a detector. Those have been the traditional uses of mass spectrometers in space. I think there may be new ways of incorporating them, as there have been technology advances that I'm not completely familiar with, two-dimensional mass spectrometry, other tandem mass spectrometry. There's a lot of approaches using mass spectrometers as a starting point and getting innovative, and then shrinking it all down. Remember, this is all very small. The units that we need for space flight, think of your toaster or your microwave oven as the maximum, and the smaller the better. So this is, again, a fit size range for small companies. I see the payloads on space missions as being the right size fit, volume fit, for what small companies can do. You don't need a clean room or a test chamber the size of the VAB. You just need something the size of a microwave oven, because the problem is intrinsically needs to be solved on a small scale.
So one last question from the virtual attendee. Define intelligent, and this person actually tried that definition. No matter which form it might exist, will be represented by separate units and consume measurable energy.
Okay, 2 points. One is, yes, consumption of energy is a thermodynamic requirement for life, and as I said earlier, that may be our only firm understanding of life on Titan, if it's there right now. And that, as I'd suggested, is the way we would approach a search for life on Titan, is search for its signature of its use of energy. As to intelligent life, how do you define it? Well, in a sense, the SETI operational definition of intelligence is, can you build a radio telescope, right? So if you apply that definition of intelligence to Earth, we became intelligent in the 60s. And I was through that era, and I agree. That's when intelligence really shone on this planet. So that would be the only answer I could give as in terms of operational answer. How do you detect it?
Thank you very much.
You bet.